Okay, so this is just me going over the answer key that I gave to you. So if looking at my work doesn't make sense to you, hopefully the kind of voiceover will help you understand it. So let's just go to that challenge problem. All right, so the way the problem starts is you have chlorine gas, it's bubbled through a solution of potassium bromide. And the question is, what is the volume of bromine produced? And a couple things we got to look out for. We're assuming that we have only 35% yield, so not even close to 100%. And they give us the density for bromine. Okay, so let's think about the way the question's asked. We're given the amount of chlorine and we're given the amount of potassium bromide, but we're asked to find the amount of bromine. So it's stoichiometry, right? Given the amount of something, figure out the amount of something else. It's stoichiometry. Now, what makes it a little bit more complicated is we're given two amounts of a reactants. So we're given a specific amount of chlorine gas and a specific amount of bromide. Yeah, potassium bromide, but we really just care about the bromide here. Okay, so not only is it stoic, it's limiting reactant stoic because we're given two amounts. Okay, so what we have to do essentially is just figure out based on our reactants how much product can we get, and then once we know the maximum amount of product we can get, that would be 100% yield. All we have to do is multiply it by 0.35 or multiply it by 35%, and that'll be what we actually get. And then the density is just once we get grams of bromine produced, we'll use the density to convert it to milliliters of bromine produced. So density is our conversion for our grams of a liquid to volume of a liquid. All right. So again, we're given two different amounts, so it's limiting reactant stoic. Okay, and at the end we'll take into account the 35% yield. Okay, so the first thing is know your recipe. Remember, your recipe is going to be a balanced equation. So based on what we were given, we have chlorine gas, and we got to remember chlorine's diatomic, so it's Cl2, is bubbled through a solution of potassium bromide, so KBr aqueous. All right. So kind of what we have to do here is predict the products. Now they gave us one of the products, so it makes it a little easier. But anytime we have an element in a compound, we should be thinking single replacement reaction. So, and the rule is like replaces like. So chlorine's going to replace the bromine. So over here, we're going to have potassium paired up with chlorine. So we'll have potassium chloride over here. And then we'll have bromine by itself. But we got to remember bromine is a diatomic element. So when it ends up by itself over here, it's going to be Br2. All right. But again, they gave us the fact that we have bromine. So we have chlorine plus potassium bromide yields bromine, Br2, plus what? That other thing would just be the potassium chloride. All right. So here is our balanced equation. So one chlorine plus two potassium bromides yield two potassium chlorides and one bromine. Okay. So we needed this equation so we could get our ratio. Now we're only focusing on the bromine here, but we have to understand that it's going to be a 1-to-1 ratio, chlorine to bromine, or bromine to chlorine, and it's going to be a 1-to-2 ratio for bromine to potassium bromide. Okay, so these two calculations here, let me zoom out a little bit so we can see them both. I'm just taking the amount of chlorine and figuring out how many moles of bromine I could possibly produce. And then in this one, I'm doing a separate calculation. I'm taking the amount of potassium bromide given and figuring out how much bromine I could produce. Okay, so for the chlorine gas, we had 35.1 liters of chlorine at STP. So if we take that volume and divide it by 22.4, that'll give us moles of chlorine, and then times the 1-to-1 ratio up here in our balanced equation, that would cancel out moles of chlorine and give us moles of bromine. So what this calculation is telling us is if all the chlorine reacts, we can get about this many moles of bromine. Okay. I'm gonna not round it for SIGDIG's purposes yet because we're not gonna round until the very end of the calculation. So we might want to maintain that. Okay. But again, if all we were trying to do was figuring out moles of bromine produced and we weren't told a specific percent yield or anything, then this is one possibility, right? right? We could get this many moles of bromine if all the chlorine reacts, okay? But we might be limited by the amount of potassium bromide. So I'm going to take my amount of potassium bromide and figure out how much bromine I could get, okay? So that would be, but in this case, we were given liters of our solution and we were given the molarity. Remember, molarity is moles per liter. So that 3.5 capital M measurement from the question, if we go back up here, remember that means 3.5 moles of potassium bromide for every 1 liter of solution. So it's our conversion, molarity is our conversion from liters of solution to moles of solute. So the first thing I'm going to do is the liters times the molarity will cancel out liters and give me moles of potassium bromide. Go back. Now, again, in this case, it's a 1, if we look up here, a 1 to 2 mole ratio. So 1 mole of bromine for every 2 moles of potassium bromide. So if we do the math there, if all of the potassium bromide reacts, we can get 2.63 moles of bromide. Okay? So if all this reactant reacted, that's how much bromine we could get. If all of this reactant reacts, that's how much bromine we can get. So this is going to be our answer to how many moles of bromine we can expect, okay, if we had 100% yield. Okay, we can't get this much down here because we only have enough chlorine to get this much. So chlorine is our limiting reactant, and if we needed to know, potassium bromide is our excess reactant. So we're still going to have some bromide left over after the reaction goes to completion, but all the chlorine would be consumed. Okay. So now let's take in the percent yield into account. So first thing, this would be moles of bromine if we had 100% yield. So if we multiply that by the molar mass of bromine, so that's where this is coming from. 1 bromine is 79.9 grams per mole, so 2 of them is 159.8. Okay. So if we do moles of bromine times the molar mass, that'll give us grams. And then here is where I'm using the density, okay? If we take our grams of bromine and we divide it by the density, that'll give us our volume unit in the density, and our volume unit in the density was milliliters. And if you go back up to the question, that's what they were asking, the volume in milliliters. So once we get grams of bromine, we'll divide by the density, and that'll give us milliliters of bromine, okay? So this would be, sorry if you can't read my handwriting, 80.774 milliliters. That would be how much bromine we could get if we had 100% yield. But remember, the question said only 35% yield. So if we take that, if we take the milliliters of bromine, the 100% yield, and we multiply it by the actual yield, 0.35%, 35%, which is 0.35 mathematically. So the 80 milliliters times 0.35 would give us the actual amount we get. So the answer to that challenge problem is around 28.3 milliliters. That's what we would expect. And we should round to 3 significant digits at the very end because all the numbers we used in our calculation had 3. Well, actually, I guess 2 because of 35% yield. So never mind, let me change that. We should round to just 28 milliliters there because the 35% yield was only 2 sig digs. So really, I should have 28%. Okay? So I hope that helps. I hope that explains it. And yeah, have a good day.